Okay, can you hear me at the back? Can you guys hear me? Good, okay. Let's get started. There's a lot to cover. So I'm going to begin a new topic today. We'll cover this today, Thursday, and the last lecture before spring break. And Project 3 will be based on the material that I teach here. So right after spring break, when you come back, that will be the project. So in the discussion about queuing and delays, you've already started to gain familiarity with the fact that as distributed systems get more heavily loaded, things slow down. And one of the big challenges is how to build distributed systems that can actually sustain hundreds, thousands, millions, tens of millions of users. So if you think about Facebook, guess what's their new name? Meta, right? I'll still call them Facebook. They cover a significant fraction of the world's population, easily 1 billion users, right? 1/7 of the world's population. That's a huge number. It's 10 to the 9. Very, very large. What do? How do you even think about building a distributed system, right? Project 1 was hard enough. Project 2, still a single user system, mostly. How do you build such a system? So that's what these 3 lectures are going to be about. A lot of valuable and interesting stuff, and I look forward to sharing them with you. First, I want to just take one moment to help you appreciate that the word scalability means different things to different people. In this class, for the next 3 lectures, we'll use a specific meaning, but I do want to emphasize it's only one particular aspect of scalability, and this is the one slide in which I will describe to you the many dimensions of scalability. First and foremost, if you're facing this problem, it means you're successful. It's a good problem to have, right? If your startup is not doing well, you will not face this problem. The problem is you can be very successful and get killed by your success. And that's the reason this is so important. The shift from just barely making it to being phenomenally successful happens so fast that unless your system has been designed ahead of time to scale properly under the conditions of rapid change, you will not be able to cope with the success, right? So this is one of those to design, to implement, to write the code, to debug the code, to test the code is on the order of weeks or months. For word of mouth and Facebook and Slack channels and other ways of communicating how cool some new startup is can happen in the order of days, maybe even hours. So there's a huge order of magnitude difference in the time scale, and that's why it's actually very, very important to think about scalability up front. So what are the dimensions of scalability? One is a very simple thing. Think about this. If I have only 5 users, getting an account for you is trivial. You ask me, I'll give you an account. All right, I'll go create it. But if you're talking about thousands of users signing up, very quickly this becomes, now I have a full-time person whose sole job is to deal with this. And people are expensive. So allowing people to create their own accounts, to sign up, all of these things, these are administrative dimensions, boring stuff. But they'll kill you if you can't scale. Okay? So various aspects of administrative scalability. The second is functional. You have many successful users, and they're all demanding, can you give us this? Can you give us that? Your competition over there has a feature that is causing everybody to say, should we switch? Before people can make that decision, you want to make sure that you can have that functionality in your system. How hard is it? How difficult is the code to modify? Right? Many, many aspects of that question. You start out only thinking your users are in Pittsburgh. Pretty soon, by word of mouth, they're all over the United States. Before you know it, a little while later, they're all over the world. Some of these users start using your system from their smartphones on 4G, or maybe even some parts of the world 3G still. Your system was tested at CMU on a LAN. Okay? It kind of is designed for assumptions of low latency, maybe a few milliseconds end to end, high bandwidth, hundreds of megabits per second. Now, some of your users have latencies on the order of hundreds of milliseconds. Some of them are trying to use your stuff from an aircraft via satellite links, where the latency is very large. So geographic scalability is the ability of your algorithms and implementation to cope with enormous diversity of bandwidth and scalability and latency across users of the system. Okay? Evolutionary scalability. You know, we'd love to believe the ecosystem of the world is stable. But the reality is it isn't. You write this code, it's working perfectly. Now they changed Java or Python. Or you get this email that says Python 2 will no longer be supported. And your code only works correctly with Python 2. Or this important feature that you relied on Ubuntu is being deprecated. They're going to do it away in the next release. Right? So it's a constantly turbulent environment. How easy is it to keep your system functioning? Remember, you haven't actually added any new functionality. You're just keeping the same thing running. And that's hard enough over long periods of time. If you are YouTube, every second today, in 2022, many hours of video are being uploaded into YouTube. Now, 1 second of 4K video is 30 megabits per second. So I just want you to think for a moment how much data we are talking about. Right? So you have the YouTube servers in the cloud at Google sucking in terabytes of data, new content, brand new content. This is you with your smartphone taking a quick video of, I don't know, spring break celebration to declare that, hey, we're done with midterms, we're heading off on spring break. Take a quick video, post it. Well, that's a few seconds of very nice video on your iPhone or your Android smartphone. That goes into YouTube. Countless people all over the world doing this spontaneously results in vast quantities of content. So the ability to scale as the content of the system increases is another dimension. Okay? And last but not least is the kind of scalability that we are going to focus on. Your system may have 1 million users. So from an administrative point of view, it's big. Each of those users may have a lot of data. So from a content point of view, it's pretty big. But you know what? At any given instant, perhaps only 100 users are using your system. The potential users don't translate to actual active users. What we're going to focus on is actual active users. And the specific form of scalability is called load scalability. How many clients can I support per server concurrently? If you log out or your testing terminates and you go home, you're done. You don't contribute load. Because I'm actively working, I'm viewing, I'm browsing, I'm making updates, I'm doing reads. How many of those can I have concurrently? Okay? So notice that as the number of users who are concurrently using the system increases, the chances are also very, very good that there's huge variation in their connectivity. Some people are at CMU, some people are at home, connecting via Fios. Some people are on a plane. Some people are in some corner of the world. First hop is 3G, and then the internet, long latency, trans-Pacific, and finally arriving at your server. So at the same instant, you have users. The more the users, the greater the diversity. It's just simple laws of probability that says as the user population increases, the chances are highly likely that they will also be diverse. So we are going to focus on this. This is the only slide in which I will mention these first 5 dimensions of scalability. But keep in mind they exist, okay? And that if you go to work for Amazon or Google or Facebook and you're asked about scalability, be clear what the person asking means, because they could mean one of these other dimensions of scalability. Okay? All right. So we have the cloud. It's a collection of servers somewhere in a big data center, exascale data center. And the requirement for good scalability is that the marginal cost of supporting an additional client is as small as possible. Marginal cost. Notice that building that big data center in the cloud was a huge fixed cost. It probably cost Amazon or Google or Microsoft tens of millions of dollars. That's just to get the foot in the door, to build the data center. But the interesting question is, if I have 1,000 users using the system and I add 1 user, what is the marginal cost? How much load? What fraction of a server does that user use? The answer to that question is critically dependent on the design of the system. So this is where you can make a tremendous difference. How smart you are in the design of the system dramatically can change this. If you are not a good designer, you won't use the techniques that we have discussed in this class. You won't use caching, you won't use prefetching. All your distributed systems will be like Project 1, which is not a very scalable design. And believe me, people make money using those kinds of systems. So remember that what I told you, that technical excellence and business success are only weakly correlated. So the bottom line is, as you grow the system, you want the ability to somehow grow the cloud resources. So let's take a hypothetical example. Let's say you have built a distributed system with the attribute that each new user, on average, based on the active workload of that user, consumes 10% of the server. Right? It's an average number, averaged over many hours of session. So once I have 10 users, I'm saturating the server. So I now need another server. And somehow I have to make sure that the second user's workload is completely handled by the second server. So now you see how this starts to get very complicated. Resources, like servers, come in fixed chunks. It's like a box, right? You can put so much into the box, but that's the capacity of the box. I need a whole new box to add more. So how do I do that in the cloud? This has been a problem since the birth of computing. If you are, say, a company that makes something, Christmas toys, let's say, well, most of the year, you have very little business. So the load on your servers is low. Nobody's doing very much. Nobody's buying very much from you. But there are 3 weeks in the year before Thanksgiving or around Thanksgiving when there's a huge spike in the demand. And if you don't respond to those clients right then, you lose their business. They're going to go to your competitor. So, in my cloud, which hosts my servers for this business, in order to cope with the peak, I have to have many servers. But most of the year, they do nothing. The alternative is to only have as many servers as are busy most of the year, and then I'm going to get killed when Christmas comes along. Which do I use? So this challenge between peak load and average load is a fundamental problem in computing systems. It's also a fundamental problem in so many other systems, even the highways. At rush hour, the highways are clogged. 2 in the morning, they're almost empty. Right? So if you look at the average utilization of the highway, it's not that much. But if you design it for the peak, that's the result that you get. So one of the really, really interesting and innovative ideas was Amazon's vision that this problem can be used to make money. That relieving the pain of having to cope with peak and average loads is a challenge every business faces. And interestingly, Amazon was the first one to face it itself. Because you all remember, Amazon started out selling books and, other widgets beyond books. They weren't a cloud provider. There was no cloud computing when they started. So everything I just said to you a few minutes ago about peak and average, they faced themselves. And so the solution that they developed, they said, you know what, this is useful to us. We can make it available to others and charge some money. And today, cloud computing is big business. Okay? So the critical insight is virtualization. That is, instead of physical servers require me to go to Dell or HP and actually buy a new machine. It has to be shipped to my machine room. It has to physically be constructed somewhere, shipped. Typically, we are talking at least delays of the order of days. Because you have to then install it, right, put the software on it, this takes time. So suppose I wanted to change the amount of resources I have, not at the granularity of days or weeks, but at the granularity of seconds. That is what virtualization lets you do. Okay? You saw this when I showed you what happens when you SSH into unix.andrew.cmu.edu. You may remember the screenshot of Scotty, and I showed you that you each get a machine. A few years ago, it used to be a physical machine inside Hall. Today, it's a virtual machine. Okay? So we're going to look at that in this lecture. So virtualization is an idea that started out with CPUs, with hardware, but it's an idea that has broadened today. So networking. I can give you your own virtual network. Storage. I can give you your own virtual disk. Right? What it gives you is an isolated world which is not affected by what other people are doing. So the insulation that it provides you can be very powerful. These are referred to as software-defined networking, software-defined storage. VMs, virtual machines, they're a 50-year-old idea, which is why they don't have the name software-defined compute. Okay, but that's what they are. The name VM was already used for them, so we don't call them software-defined compute. Okay. Something very, very important, and this is the business innovation that Amazon created, is that virtualization can transform capital expenditure into operational expenditure. So at CMU, for example, any expenses for articles costing more than $5,000 is considered a capital expense. So if I, for my grad students or my lab, I want to buy a big machine that is maybe $20,000, there are special permissions I have to get, first of all, to do that. And if you're a company, if I spend $10 for something, I deduct the $10 as a business expense, the cost of running the business. If it's a capital expense, I cannot do that. The assumption is that capital expenditure is spread out over time. So a car, an aircraft for an airline, a house or a building, a business office, an expensive computer, all of these things which are big ticket items, the assumption, the accounting, is such that you cannot deduct the full cost of it this year. You have to spread it out, and this starts getting very quickly into fairly complicated accounting rules. Some things have 5-year lives, buildings have 30 years. Right? So the rules differ for what kind of article you're talking about. But the point is, capital expenses. If you're a small startup company, for me to have to buy a bunch of machines to cope with my peak load, and I have to put all that money up front, and I can't even deduct it all as a business expense, right? It makes my life very hard. On the other hand, what Amazon says is very simple. It said, dear startup, don't worry. You don't have to buy a single machine yourself. We'll buy it. You just rent it from us. It's the same way your landlord in your apartment works. He owns the building. He worries about the repairs. He pays the city taxes, the county taxes. Right? You never see those things. What you pay to him is a monthly rent. But at the end of the day, built into that rent is profit for the landlord. The total expenses, all of these other things put together, including the depreciation on the building, is less than the rent that you pay him by a substantial amount. That's his profit. Same story with Amazon. Okay? They are the landlord of the real hardware. You're the renters. Homes, apartments, you rent by the year typically. Virtual machines, you can rent by the minute. So the time scale, is off by a factor of 100 or something, but other than that, the idea is no different. So the fact that this is phenomenally successful shows you that this is an innovation. It's an example of an excellent technical innovation that has been translated into a powerful business example. So this is one of the rare examples where technical excellence and business success went hand in hand. Right? So it's a good exception to the general rule that I mentioned to you. So the ability to flexibly allocate resources is referred to as elasticity, and Amazon's name for the very first product that it offered was EC2, standing for Elastic Cloud Compute. Okay? So, given how important virtual machines are, I'm going to take a moment to drill down a little deeper. What are these things? How do they work? How do they come about? Amazingly, like so many other ideas in computer science, the roots of virtual machines go back much, much, much further. It's older than distributed systems. And distributed systems are already 50 years old. Okay? This thing dates back to 1967. So in that era, on the first day of class, I showed you this slide, this picture. This is a mainframe from the 1960s, IBM mainframe. Your smartphone has more power than that room full of mainframe computing. Okay? So, that's a quote that I'm often fond of using, that victory has 1,000 fathers. So there are many reasons for why virtualization came about, but the one I'm about to explain really has historical basis. That machine was extremely expensive. Your smartphone is a couple of $100. You can buy one for a few $100, Android. iPhone might be a little more expensive, but still something that a student can purchase. That thing was millions of dollars, something like one machine for all of CME or two machines for all of CME. That's a scale. And there was definitely capital expenditure. So I want you to think about this. Suppose you are the manufacturer of that computer, IBM. They made those things. Their developers have to write the code for the operating system. Who else is going to do it? Their software developers. How do they debug that code? Because to debug operating system code, I need the machine, but there's only one. So the way it worked was Will over there, you get the machine from midnight to 2 a.m. And Murphy will make sure that at 11:59 or 1:59, just before you have to hand that machine over to Abby, right? Just at that moment is when the bug that you've been pursuing for 2 hours just looks like it's going to be solved. But you have to hand the machine over. And tomorrow, you aren't able to recreate the bug. Can you imagine how painful it would be? That was the pain. It was extremely painful. In fact, if you haven't read this, I encourage you all. How many of you know of this book, The Mythical Man Month? Only one person in class has heard of this book. I encourage all of you to read this. It's one of those perfect books thin paperback to read on the flight to spring break. Light reading, easy reading, right? But full of wisdom, full of horror stories about software development, right? One of the most famous lines from this book is adding more developers to a project that is behind schedule is guaranteed to delay it further. Right? All these lessons that today are considered part of software engineering, these people were the first to encounter them, learn about them, and write about them. Okay? So it's a great book to read. So I just gave you an example of how the fact that machines were expensive and hard to come by made software development very difficult. What are you going to do? You can, Will could make a deal with Abby. Abby, how about I take another 2 hours tonight, but you can have my 2 hours tomorrow. Right? Things like that. You'd have to work out deals. Life was miserable. So somebody came up with the idea, why can't we get a computer to make clones of itself? The concept of simulation was well understood by the late 60s. People used simulation for all kinds of things. They said, well, why can't I create a program that simulates itself? In fact, the simulation has to be so perfect that even operating system code cannot tell whether it's running on the real system or the virtual system. If you have successfully created such a program, you have created a virtual machine. And the people who succeeded in figuring out how to do that were these people. Now, what is brilliant is if we had solved the problem in 2022, the solution wouldn't have been anywhere as good. The reason is because today's machines are so fast that a lot of slop and inefficiency can be hidden. But the machines of this era were so slow that in order to debug operating system code, many of your bugs are race conditions. If the timing is changed too much, the race condition just disappears. You can't debug it. You can slow down the components by a modest amount and it probably can still manifest the bugs. So probably 10, 20, 30% slowdown, you might still succeed. But if it was a factor of 2 or 3 slowdown, you're dead. So circumstances forced these people to come up with implementation techniques that are used till today. In 2022, we still use the techniques that they used to create virtual machines. A few things have changed, but the basic ideas are still the same. And the net effect was that the virtual machines that they created had only a small inefficiency, maybe 20% slowdown. User code that is application code, ran at full speed. No slowdown at all. The only time slowdown occurred is if you made any system calls to the operating system for I/O, or displaying something on the screen, or reading something from the network, or printing on a printer. These are the kinds of things for which you had to invoke the operating system. Those parts of it were slowed down a bit, but your application code ran at full speed. Okay? So we don't have the time in this class to sort of drill down into how exactly you do this, but any of you who are interested, this is amazingly cool stuff. So learning about virtual machines is typically done in an architecture course, and possibly in an operating systems course. So both of those are good places to learn. One of the huge wins of a virtual machine is that you can have many of them. One of the virtual machines can be running Windows 10. The other virtual machine can be running Ubuntu. The third one can be running Red Hat Linux. I can have them all concurrently executing on the same platform and doing it without one line of change to any of those pieces of code. That is truly amazing. And it's the reason virtual machine technology has proved to be so successful. So if you look at the history of virtual machines, it's got to be among the weirdest histories. So I just gave you the birth, right? So mid-60s, everybody thought virtual machines were cool. And by the early 70s, there were commercial products, operating systems that used them. You could actually use them, and I have. I've actually used this system. But then something happened. By 1981, Apple initially, but then IBM PC, created the personal computer. In a few years, people said, wait a minute, what do I need a virtual machine for? I can buy a real machine. It only costs me a few $1,000s. I, as an individual, can buy it. It's cheaper than a car. And people buy cars. It's no longer a capital expenditure on the same scale as that mainframe. So, if you were a PhD student in the mid-1990s, and somebody said, what are you working on for your research? And he said, oh, I'm working on virtual machines. People would look at you pitifully, like, oh my God. You know, it's like you're working on dinosaurs, right? Some ancient stuff that nobody uses anymore, and you kind of nod pitifully and move on, try to be polite. But then by the late 1990s, virtual machines became hot again. And today, by late 20s, they are extremely important today. So I know of no other abstraction in computing that has this property. So how is it an abstraction can be useful for 60 years? I can't even imagine how many orders of magnitude speed up that represents by Moore's law. Some, compared to the smartphone, right? It's more powerful than that mainframe that I showed you. So what is the secret? So it turns out that virtual machines, the way they were invented and the way they've evolved, happen to have a property that is amazingly powerful. Okay, and that property is that they are able to execute legacy software unmodified. Legacy software. This stuff that has worked for 20 years, okay, is so important to you, you can't give it up, but it only runs on this machine. I can virtualize it, put it on a new physical machine, and finally get rid of the old machine. As far as the software is concerned, it thinks it's still running on the old machine. That capability turns out in the real world to be enormously powerful. At different points in time, exactly where the pain point is has shifted. So 60 years ago, the pain point was the cost of computing hardware. One machine was millions of dollars. That was pain, severe pain. Today, that's not pain. You buy a faster machine every time you change your smartphone. Today, the pain point is what is called total cost of ownership. If you add up all the number of hours you spend keeping your Windows machine up to date or your Ubuntu machine up to date, add it all up and multiply it by some number of dollars per hour, it'll end up being more expensive than the cost of the machine. Right? That is what has happened. As machines have grown cheaper, the human cost has ended up being much more expensive. Well, I started this lecture by explaining to you how cloud computing benefits from virtual machines. What it lets you do is on demand create instances of resources. So the pain point today is management. Cloud computing reduces the cost of it by centralization. Instead of lots and lots of dispersed physical hardware, you have one big data center where a small number of operators can administer all those machines. And those resources can be virtualized and used by the average user. That ability is the current pain, but it solves that pain. And it does so while protecting legacy investments. So if you have something that depends on this old, crufty software that nobody uses these days, but you know what? It's too expensive to rewrite. The two guys who both understood that code are both dead. You can't hire them. There are no replacements to be found. It was probably written in COBOL. Right? Or Fortran, yeah. Right? But the code still runs. It works well enough. Right? You would like to believe that such things don't exist. Believe me, there's plenty of this. And last but not least, it solves the first two problems in a way that is quite robust and stable. So it's not a temperamental solution that needs constant tweaking. Actually runs pretty stably. So this fact that regardless of the shift in pain point, the ability to gracefully allow you to transition your legacy software to a new world, whatever the new world is, that solves the pain point, that is the powerful capability of virtual machines. And that's why they are so successful. How many of you know this marketing metaphor of marketing aspirin versus marketing vitamins? You know it. One person knows it. That's it? You're not pulling my leg, right? Really? You've never heard of this? Okay. This is actually not a computer science metaphor. It's a Tlrrs metaphor, but it's still useful. It's always easier to market aspirin than it is to market vitamins. Okay, here's why. To sell vitamins, you have to go make the case. Look, if you take these vitamins regularly and you do workouts and you do X, Y, and Z and lead a healthy life, then these vitamins will do you good. Right? So when is the benefit? Many years in the future. Okay? I have to pay for the vitamins now, but the benefit is many years in the future. When do you ask for aspirin? When you have a splitting headache. You are feeling pain now. That aspirin solves your current pain. It's a lot easier to sell people aspirin. Okay? So, based on that, virtual machines fall into the category of aspirin. They solve your current pain. They say, yes, your code is bad, it's horribly written by people who didn't take 15440, okay, is written in a programming language that no one knows anymore. But you know what? While it takes you 2 years to rewrite the code completely, we will keep your business going by virtualizing the machine and the environment and keeping it going until you can replace it with something better. That bridge, that ability is very powerful in the real world. It's not pretty. Okay, headaches are never pretty. But they're extraordinarily valuable as a problem to solve and as a capability to solve. Now, exactly what kind of legacy investment we're talking about can vary, right? I've given you some simple examples, but you can go see in the literature many different use cases and case studies of how virtualization has been used. Now, one of the interesting points also relates to the fact that virtual machines were invented in an era when hardware virtualization was important. Today, you have things like Java Virtual Machine, JVM. You have things like Dalvik Virtual Machine, which abstract the Android environment. When I say virtual machine, I don't mean these kinds of things. These virtual machines will never give us the benefits that these old-fashioned virtual machines give you. And the reason is so counterintuitive, okay? Very, very counterintuitive. Here's why. Basically, here is how all of these virtualizations work, okay? You have some kind of legacy world, right? Old code, old applications, written in programming languages that nobody knows, right? This is old stuff. This is the new solution designed to relieve whatever is the current pain point. So cloud computing is an example invented, as I explained to you, to solve the CapEx versus OpEx problem, to solve the peak versus average problem, right? So this is what cloud computing infrastructure gives you. What virtual machines do for you is through a very stable hardware interface, they connect these two worlds. They allow you to run legacy code in a brand new environment. So your old, crafty COBOL code can be running in Amazon in a virtual machine. The actual hardware on which it runs is modern hardware. But to the code, it's probably emulating some ancient machine, which is the last machine on which that COBOL compiler worked. Okay? Now, interesting question is, what makes hardware special? The same picture applies to Dalvik VM, Java Virtual Machine, all of them, but none of them work as well. Why is that? Well, the reason is very simple. The success of this picture depends on the narrow waistline. Okay? Ideally, almost a single point. The narrower, the better. The narrower this is, the more combinations below can be used with combinations above. As the interface widens, you now have to support that entire interface. A narrow interface says, all you have to do is to look like IP. For example, okay? As in real life, waistlines have a habit of expanding. How is that? Why is that? Very simple. Imagine, let's say you work for Microsoft. Microsoft runs the operating system, Windows 10, but it also develops applications that run on that operating system. So SQL Server is the SQL database that Microsoft builds. Azure is the cloud software. Office 365 would be all use, PowerPoint, Word, etc. All of these things. Now imagine in a competitive situation, somebody is going to choose between Oracle and SQL Server. And they're going to make the decision based on a couple of important benchmarks. Whoever runs that better is going to get this multi-million-dollar contract. Now, if you are the head of the team for SQL Server and you know of an important operating system optimization that would help your software, go talk to your buddy in the Windows group and say, hey, can you add this feature? Only I need to use it. Pretty soon, by feature creep, you have widened that waistline. And what makes it worse in the kind of scenario I described, much of the width of that waistline is not even described publicly. So if you Google for the undocumented Windows interface, you will find many hidden treasures that are not part of the official standard that were created in this way. Okay? Now, in theory, you could exercise rigorous discipline to make sure that the waistline doesn't expand. But we all know how far the discipline goes. Right? Not easy. In the real world, depending on hardware means changing it is a lot harder. Right? I have to go convince Intel to make changes to the hardware. And Intel has to produce chips. Those things take a long time to debug, produce. I mean, we're talking 10 years, 5 years, okay, but not 1 week. I can make an operating system extension to widen that interface in software in 1 week. So the malleability of software as opposed to hardware is the real reason that virtual machines that target the hardware interface have proved to be so successful. It's the inability to change them easily that has proved to be the reason for their success. Okay? All right, so I've already covered all this. Here's an excellent example of the point I just made. As interfaces get wider, your abstraction becomes very brittle. Right? It's like something with many moving parts, all of which have to perfectly match. It's an and. So any one thing that's a mismatch kills you. Right? The fewer the number of terms in an and, the more likely you can keep it going. A simple idea. So here is an example. So the very first example of process migration, okay, where I have a Linux process, for example, and able to say, I want you to go from this machine, this client, to that machine. And it moves itself over the network and executes over there. And then you tell it, I want you to come back, and it comes back. Right? Brilliant vision. It dates back to 1983. I was at the conference where the talk was given. Right? Very cool system. Roughly every 5 years, since 1983 until today, there's a PhD thesis somewhere in the world on this topic. The most recent that I'm aware of is from December 2021. Okay, and it's not even completed. It's supposed to be completed in 2023. So you would think that any idea that is capable of producing a PhD thesis every 5 years for, how many years is that? 40 years, almost, right? There's something strange about it. And indeed, what is very interesting is that not a single operating system today supports process migration. There are any number of experimental operating systems, but it's not a feature of Windows, it's not a feature in Red Hat, Ubuntu, none of them. The reason is because it is a brittle abstraction by its nature. That waistline is very wide. All of the things that a process can do relative to its operating system, all the system calls that it makes, one of them changes the abstraction bricks. In contrast, virtual machine migration was first demonstrated in 2005. It is now standard in every single product of Microsoft, of VMware, Citrix, and it's used every day in data centers worldwide. Because the abstraction of process migration is the same abstraction as virtual machine migration. The only difference, in many ways, virtual machine migration seems stupid. Why move this huge, monstrous thing? I just have to move this tiny little process. But it turns out that moving the virtual machine results in a lot more stable solution, which I don't have to worry about maintaining. Process migration will work for 1 week, after which the very first Windows update or Ubuntu update can cause it to break. And the amount of time it takes to keep it working turns out to be quite a lot. Whereas with the virtual machine, x86 hardware hasn't changed a lot, especially if the virtual machine targets the core functionality of x86 rather than extensions. And that's the reason that it works well. Any questions before I move on virtual machines and all of the stuff that I've talked about? Okay. Have you studied this stuff in any other class? It's all new stuff. Do you find it interesting? Yes? Okay. All right. So, here's what a virtual machine looks like. There's just a minimal background, okay? There's a piece of software called a virtual machine monitor which creates the illusion. It's called a VMM. Okay? The virtual machine, as I mentioned to you, is a perfect software abstraction of OS visible hardware. This is very important. It's not just user application visibility, it's operating system visibility. Low-level grungy stuff inside the machine. Hardware registers, translation buffer table, caches, disk I/O, all that ugly stuff that we nicely abstract away. Here you have to correctly emulate all that. So if you look at it, the physical hardware and any software, the lowest level, is referred to as the host. The software responsible for creating the virtual machine illusion is the VMM, virtual machine monitor. And then the virtual machine itself typically has an operating system like Windows or Ubuntu inside it. That's called the guest. And then on top of it is an application. And if I'm emulating one kind of hardware or another, for example, if I want to emulate an ARM smartphone on top of a Xeon Intel server hardware, then I would have an extra piece in here, which is the emulator for ARM on top of x86. Okay? This assumes that the guest is targeted for the same hardware as the host already is. Okay? Now it turns out that there are two flavors of virtual machines. And the names of historical origin, there's no logic to these names. A type 1 hypervisor, of which VMware ESX, a very well-known, widely used hypervisor, XenSource is another. Here, the bare metal host is what is used. All of the virtual machines are directly running on the bare metal with the virtual machine monitor as the only piece of software that exists. So there's no underlying operating system. This doesn't look like a desktop. It can only be used as a server. Okay? A type 2 hypervisor, your laptop or your desktop, provides the host operating system. And on top of that, you have a virtual machine monitor, and the virtual machines are created on top of that. Those are called type 2 hypervisors. And VMware Workstation, KVM, if you're using Linux, VirtualBox. Some of you run Windows applications on top of your Mac, right? That's how you do it. The software, what's it called, a parallel? Right? That's the name of the proprietary software that does it. It's basically a virtual machine capable software. This is how it works. So the actual Mac OS code from Apple, unmodified in binary form, executes inside an environment that looks to it like it owns the whole environment. Okay? So, virtual machines, as I told you, are 60 years old. For the use cases for which it was originally invented, it worked perfectly fine. But as it started getting used in cloud computing, remember the point I made at the start of this lecture. The marginal cost of adding a new user is key. Now, virtual machine is not a lightweight abstraction. It's a pretty heavyweight abstraction. Right? You're emulating an entire machine, not just a small part of it. The net effect is that the memory resources and processing resources needed to emulate it are quite substantial. So, as cloud computing became much more widely used, people started asking, is there a way to get much of the benefit of virtual machines without paying such a high cost, especially in memory usage? Okay, because if I have a virtual machine with a 2 gigabyte address space, then I need 2 gigabytes allocated from the real hardware. If my whole machine is only 32 gigabytes, I can probably make 10, 15 such virtual machines, and then I'm done. I don't have any other physical machine to carve up. But what if I wanted 100 virtual machines? What do I do now? Right? So the very expensive resource usage of virtual machines caused people to think, are there lighter weight abstractions? And so that has led to what are called containers. Containers are like a poor man's virtual machine. They don't have all the attractive properties I described to you in the previous slide. You cannot run 50-year-old software on it. COBOL, no, sorry. The range of supported diversity is much smaller, okay? However, it has a much smaller footprint. So, containers, and the best known of these are a specific kind of container called Docker. It just happens to be the company that makes them. But they are actually supported in Linux. It's open source code. What is different is there is no, in the picture I showed you here, there's a host layer and a guest layer. There is no such difference with containers. Okay? There's only one operating system, and the container code inside the container uses the same operating system resources. So because of that, and because the container doesn't have its entire address space, the memory footprint of containers is much smaller. Okay? And the net effect is you can virtualize a portion of your hardware, a portion of the file system. You can use the scheduler to allocate portions of the CPU. Like, for example, if there are 32 cores, I can restrict the number of cores that are allocated to your container. Okay? Question?
Is there any connection between how container virtualization works and process migration?
You know, good question. You would think there should be a relationship. People have tried, but it's never been successful. Okay? In fact, I think I mentioned that on my next slide. Where do I have it? Yeah. No container migration. Kill the old one, copy the state. So you kill the old, you transmit the memory and disk state, just, and then on the new machine you create a new container that starts from there. So it's not migration, it's like kill and reincarnate. That's the approach that is used. That works. Attempts to actually do migration, at the end of the day, they've turned out to be harder to implement, less efficient than imagined or hoped for, and ultimately not very successful. So yeah, it doesn't break the process migration bottleneck at all. It's a good question. Somebody else had a question? Yep.
The first point that you said as lacking in containers.
This one? Or here?
Yeah, you said it can't run the cobalt stuff, but why is that? I think.
Oh, because the operating system itself might need to be different.
But you have different container images for.
No. If I have a Windows laptop and I use containers, I can only run Windows programs in them. I can't run Linux programs.
Oh, but I can pull a Ubuntu container and run it on top of my Windows.
Usually that's not possible. In the specific case of Ubuntu, Canonical has worked with Microsoft to create Windows operating system support for Linux. It's called Windows for Linux.
Okay.
Unless you install it, that container, Ubuntu container, will not run. Okay? So what you've taken is an operating system, modified the operating system, and then you are using part of it from the container. Whereas with the virtual machine approach, you don't have to touch the lower-level operating system. Okay? The entire operating system that you need is running as a guest. So the fact that Ubuntu containers exist on Windows is is not in any way disproving what I've said here. What is happening there is Canonical has actually implemented inside Windows. If you Google for Windows for Linux, it's a huge subsystem of many thousand lines of code that they've written. So they've actually modified the operating system. So
there's no chance that the hardware instruction translation would happen on a container?
No. There's no magic. If you want that level of independence, use virtual machines. If you're willing to live with the limitations of using only the operating system resources on that machine and living within those restrictions, and you want smaller memory footprint, containers work. So there are two different solutions. You have to be very clear-eyed about why you're using one or the other. Okay? Also mentioned here is that the complex interface also offers a wider attack surface. So the number of security vulnerabilities are much, much higher with containers. You can think of virtual machines like a fortress with a thick wall, okay, that's hard to penetrate. It can be penetrated. I mean, there are attacks. It's a lot harder and a lot more inefficient. Okay? Containers are like thin bamboo walls. They can be penetrated more easily. There are many more attacks that can be mounted. Okay? Let me go back. Whoops. Yes?
I have one more question.
Yeah?
One of the previous slides mentioned para-virtualization. Could you explain what that is?
I believe, I forget which one. Para-virtualization is a weird concept. Okay? It says some portion of a hardware abstraction is too hard to emulate perfectly, so I'm going to not emulate it, but I'll modify the operating system, the guest operating system, to cope with the change. So it is deliberately weakening the virtual machine abstraction for reasons of either performance or implementation complexity. Okay? When I say virtual machines, I mean rigorous, hardcore, no para stuff. Okay? Okay, I think I finished most of this. These are some results from recent papers, so SOSP 2017. It shows, on average, as the number of guests increases, up to 1,000, the cost of creating a container still remains around a little over 100 milliseconds. Notice that the y-axis is log scale. Okay? This is the cost of creating a new virtual machine. It increases exponentially as the number of concurrently running guests increases. Okay? So very expensive. And this shows you latency for various interactions in microseconds. Red says basically 200 millisecond latency, and you notice that the blue, the green, and the red are almost coincident. It says containers essentially give you the same I/O performance as running on bare metal. Virtual machines, on the other hand, cost you a lot more. This is the cumulative distribution function, right? So that's why the shapes are what they are. So these are both examples sort of substantiating the fact that that we have much lower overhead with containers. So at the same time, remember that these things have got strengths and weaknesses, okay? Containers are much harder to implement in many ways. I've already mentioned the attack surface. They're more vulnerable to bugs, security. There's quite a bit of configuration work. The virtual machine, I give you a bare metal machine. It's like giving you a piece of hardware from Dell or from HP or from Lenovo. That's it. You get to use it. Here, for containers, there are lots and lots of configurations. If you get them all right, yes, you'll have a well-running system, but it takes a fair bit of time to figure out all the right settings for these containers. I've already mentioned points 4 and 5, less general. In particular, can only, that should be operating. This is a spelling correction from PowerPoint that was not quite right. Operating system. I've already mentioned migration is really not feasible. And something else that people have noticed is in order to support containers efficiently, you end up tainting the state of the underlying host operating system. That, in other words, if you care a lot about privacy and you don't want state from inside a container to leak out, that's very difficult to achieve. Almost always, some of that state does leak out. Okay? So this is a good point to stop. I have 5 minutes, and in that 5 minutes, I will address one other thing. But before I do that, any questions on this before I move on? Yeah.
I don't understand what is the virtual machine monitor.
Say that again.
What is the virtual machine monitor?
What is the virtual machine monitor?
Yeah, what it does?
It's a piece of software which creates the illusion of virtual machines. I have a piece of hardware. It's one physical box. Somehow, somebody manages to create 16 virtual machines out of this box. The piece of software that does that is called the virtual machine monitor. Okay? Okay, so in the 4 minutes I have, I wanted to address something totally non-technical. So there have been a lot of piazza posts about, oh, it's painful, and oh, can you move the midterm later? Can you move the deadlines later? Now, I believe that you're a brilliant class, okay? You're no less smart than students who have sat in these seats in the past 6 years. Okay? If anything, you're smarter. You're just hardworking. You're perfectly capable of coping with all these deadlines, okay? Here, 16, 17, 18, 19, 20. I left out 21 only because it was all done under Zoom. Because of COVID, there was no midterm exam, so different, okay? But all the others, if you notice horizontally, within a few days, she agrees with me. See? So, you are perfectly capable of doing this. I understand it's a work, but at least 6 previous generations of students have done all of this and done superbly. I have complete confidence all of you will do that too. Okay? See you on Thursday.